In Concept A, we're going to be discussing the phases of matter. You've already been exposed to this in a variety of other science classes, so we're going to take a look at it as we start our next unit. Tomorrow, the goals in class are going to be to be able to distinguish between the three main phases of matter that we're going to be discussing based on their properties, also representing them with particle diagrams and analyzing the particle diagrams. And we also want to be able to start to relate these phases of matters to intermolecular forces, and eventually we'll also tie in how pressure and temperature affect them. So matter exists in three main forms. We've talked about these before in the notations for them. S meaning that we have a solid, liquid, and then G representing a gas. In this case, we can see that we have pure samples here, a pure solid sample of water, a pure liquid sample of nitrogen, and so on. So we're representing the three main forms here. Now, we have used the notation of AQ, aqueous, but however, this is a solution, which is simply a solid dissolved in water. This is a state of matter, but not a phase. So you're only going to be hearing us focus on solid, liquids, and gases because a solution is really just a mixture. Now, in the last unit, we talked about intermolecular forces of attraction, and now we're going to relate that to how these influences what phase of matter a substance is. Phases of matter are simply different stages of attraction. Now, the stronger the attractive forces, such as hydrogen bonding, which we've discussed, the closer the particles will be from each other. The weaker the attractive forces, like van der Waals or London dispersion, the farther apart the particles will be from each other because there's not anything holding them together. Alright, so let's focus on solids. Solids have a definite shape. That means that they're not going to change their shape based on what container we place them in. They're going to hold their shape. Same thing with volume. No matter what environment or as long as it's the same temperature and pressure conditions, it's going to have a definite volume. Again, it's not going to change based on the container that I place it in. Now, solids, while it looks like particles are moving, there is actual particle movement. They vibrate about a fixed point. So particles are locked in a crystal lattice in this geometric pattern, and while they are locked in place, they do vibrate in that locked place. Density, we have a high density, so there's a very small distance between solid particles. Talking about the attractions between particles, at room temperature we have a strong attraction between solid particles. And in our particle diagrams, again, you should see that geometric pattern, nicely, neatly organized, packed in close together, and again, being held together by these very strong IMFs. Now with liquids, they do have an indefinite shape, meaning that their shape does change based on the container that we place them in. However, the volume is going to stay constant, no matter where I place it. So just because I move it from one container to the next, while it may change shape, the actual volume of the liquid is not going to change. Now with particle movement, it's similar to solids in the fact that they do vibrate. However, they're vibrating about moving points. Meaning, we like to describe particles in a liquid as being able to flow around each other, still close together, but having that additional movement compared to a solid. Liquids do have a high density, not as high as solids, depending on the material that you're talking with, so they do have a fairly small distance between particles. The IMFs are still considered strong. However, you can see in the particle diagram, they're more disorganized. They've lost that geometric pattern. So we represent them with kind of a little bit more chaotic, but still close together organization. Now with gases, these have both an indefinite shape and volume. Gases are going to fill whatever container we place it in. It will also take the shape of that container. Now with particle movement, these have basically the most freedom. They're free to move around the container. So they have the most freedom. They're the furthest particles apart from each other. So with densities, we talk about gases having a very low density because of the large distance between particles. With IMFs, they tend to be weaker IMFs. That's why they're able to exist, their particles so far apart. And with particle diagrams, we like to draw gases taking up the entire shape and also moving around far apart from each other to represent appropriately the gas. And here you can see some different examples looking at some zoomed in particles. Now, besides the nature of a substance and the types of IMFs, a phase of a substance also depends on temperature and pressure. So let's talk a little bit about what those means. Remember, we've already discussed temperature way back in September. Temperature affects the motion of the particles. The faster the particles are moving, the higher the temperature. Because remember, temperature is really a measure of the average kinetic energy. And kinetic energy meaning motion. Now, pressure we haven't talked too much about. Pressure is the force per unit area. So how much force do you have spread out over a certain amount of area? So force is how hard you push. Pressure is how spread out that push is. So we use a couple different units for pressure. Atmospheres and kilopascals are the most common ones that we'll use in this course, but there is also torricelli and millimeters of mercury that we'll be discussing. These are all related to each other. Make sure you get this down. So we can do conversions between different units of pressure based on these various equalities. STP, you guys have seen this, you've asked me about it because it's come up in multiple choice questions. STP stands for standard temperature and pressure. Standard pressure, which is on the front of your reference table in Table A, is 1 atmospheric pressure or 101.3 kilopascals. So when we talk about a substance being at standard pressure, we're saying that it's at 1 atm. Standard temperature is 0 degrees Celsius, or which is also equal to 273 Kelvin. So when we say a substance is at STP, we're saying it's at 1 atm and 273 Kelvin. All right, well, that's it. We will continue on with going over phases in class tomorrow, and then our next concept is going to be phase changes and how energy and IMFs affect those.